Hi guys, this is topic 3.13, a Beer-Lambert law. Today's objective is to explain the amount of light absorbed by a solution of molecules or ions in relationship to the concentration, path length, and molar absorptivity. You did this lab in the beginning of the semester in Unit 1. So, in terms of absorbance, you have to also look at what may cause the absorbance to increase or decrease in your readings. One way to measure the concentration of a color substance is by seeing how much light is passed through it or how much light is stopped. So this is referred to as the absorbance. A spectrophotometer or colorimeter can be used to measure the absorbance. So essentially you have a light passing through, and then you have your sample, there's a detector, and there's a digital output that's read. The more concentrated the solution is, the less light that can pass through. Concentration is looking at the amount of particles in solution. Another word that we use to describe concentration is molarity. Molarity is the moles of solute divided by the volume of solution. Your solute is what is being dissolved. Your solvent is what's doing the dissolving. Combined together, that's your solution. If it's a solution in water, it's described as aqueous. The unit for molarity, capital M, is moles per liter. So we see this, we're looking at it's a general image of decreasing molarity. So decreasing molarity means that it's going to be a lighter color in terms of the solution. So different colors of wavelengths absorb different colors of light. You're going to need to know these wavelengths and colors for the most part. Usually it's provided in the question, but I've seen it to where you have to memorize the wavelengths as well. So maybe get the general intervals and then try to get those down as much as you can. That would be good. So if we're using a red solution, we should choose to use green light with a wavelength of 560 to 520 nanometers to measure it. We have to look at our complementary colors, our color wheel. So for colored solutions, absorbance can be used to measure the concentration of solutions. First, you need to determine the best wavelength to use to measure your sample. To do this, you'll place your sample in a spectrophotometer and generate a graph of observance versus wavelength. The best choice for a wavelength is one where the absorbance is close to 1. So based on this, the closest to 1, it's 620 nanometers. Then you create a calibration graph with some standard solutions like y'all did in the lab and their corresponding absorbance value. You should have a linear graph and have your slope, and it will give you your molar absorptive constant, and that's the one that looks like an E in the Beer-Lambert law. So your absorbance, capital A, equals a molar absorptive constant, which is your slope, times your path length, usually 1 centimeters, but they would tell you otherwise. Then your molarity is your C is concentration or molarity. So if you look at it this way, if you increase your path length, meaning your cuvette will be larger than 1 centimeter, and everything else is the same, your constant as well as your concentration, your absorbance will increase if you increase your path length. Then you can measure the absorbance of an unknown. When you calibrate your spectrophotometer, you should start with a blank, and the blank is your solvent only, usually water. By creating or calibrating the spectrophotometer with the blank, it will remove the data from the solvent and therefore only outputs the absorbance of the solute. It kind of subtracts it out like a tare button on a digital scale. So apparently my stylus isn't working, so I will have to figure out a different way to show this to y'all. But I will post an image of the work for this on your Google Classroom. You can look at the image to see how to solve it. But we're going to use our A equals our molar absorptivity constant times my path length times my concentration. and I have to solve for concentration by using the absorbance in the question, the molar absorptivity, and the fact that our path length is 1 centimeter, and I will get my concentration. I'll post that on your Google Classroom. What would cause A and B to occur? So that means what would cause your absorbance to be artificially increased or decreased, A and B. So some things that can cause A and B to, or absorbance to increase or decrease. So some examples may include, for increasing your absorbance, using a cuvette that previously contained a higher concentration of your substance. Maybe even having smudges on your cuvette or scratches on your cuvette that will artificially increase your absorbance. So that would be A. For it to be B, it's possible that if you may get an artificially low absorbance. Maybe you made your solution incorrectly and your concentration is actually lower than what you thought it was. Sometimes, if you rinse out a cuvette with water before you're adding a sample, that may actually artificially lower your concentration, because you may have some leftover residue of water in the cuvette that can decrease the concentration. Decreased concentration means decreased absorbance, potentially. So determine the effect of the following errors on the measured absorbance for a peak colored 0.50 molar solution of cobalt 2 chloride. The spectrophotometer was calibrated with 0.05 molar cobalt 2 chloride solution instead of water. So what happens here? What happens with your absorbance? So I know I mentioned if you rinse something with water, it may decrease the absorbance, but if you actually calibrate your spectrophotometer with something else besides water, and notice how it's a lower concentration than what you have, what you're what you're actually doing is you're going to actually end up creating an artificially decreased absorbance when you're doing your readings. And this is because you're kind of subtracting out the 0.05 from the 0.5. Because if you use the water, all you're removing, technically, you're tearing is the clear solvent, the water. But if you actually put 0.05 molar solution, you're actually going to subtract out 0.05 molar solution from your 0.5 molar solution sample. All right, so if you have any questions, please let me know. Thanks, guys. Hit that like and subscribe and all that type of stuff. Bye.